Our first speaker today is Matt Hansen, and his presentation is on coaxial elastomeric socket for Crosstalk. He is a VP of Sales and Marketing at TSC Works Incorporated. It's a wholly owned subsidiary of TSC Company Limited. And Matt began his test consumables career in 1997, and he is spanning more than 20 plus years and held global sales and marketing positions with leading manufacturers of IC, test sockets, load boards, and probe cards. Matt holds a Bachelor of Science in Business Administration, Marketing from San Jose State. Welcome, Matt, and please go ahead with your presentation.
Great, thank you very much. I want to thank the committee and the sponsors. Also, I want to thank my colleagues who did all the real work for this paper, Yunchan, Chengsu, BoHyun, Seungho, and others. Okay, let's see. Okay, so today we'll basically talk about data rate trends, crosstalk, types of sockets for final test, and then we'll introduce a coaxial elastomer socket, and then talk a little bit about performance comparisons. So as everyone knows, data rates continue to trend more and more data since 2010. Basically every 1 to 3 years, depending on the application, you're seeing a doubling of data rates. So in the case of PCIe, we're expecting 64 gigabits per second by 2023. And in the case of GDDR, we're looking at 16 gigabits per second by 2021, or at the end of 2021. So crosstalk, of course, is an electromagnetic interference phenomenon that occurs between two circuits and conductors. When high-speed signals are transmitted through a conductor, an electromagnetic waveform is generated around the conductor, which can adversely affect adjacent signals and degrade signal characteristics. This can cause bit errors and false switching, for example. And as pitch gets tighter in packaging, then so too does the problem, or it becomes a bigger problem. Everyone's familiar with the standard coaxial cable that you might find in your home. This consists of a shielding layer, an insulating layer, and a center conductor. We use this for very high data rates in our homes for cable TV, for example, or for our ISP service provider. Types of sockets traditionally have been spring probe. Of course, there's stampings and other types of things, but spring probes have really become a mainstay. And then as things got quicker and more complicated and more expensive, then too came elastomeric test sockets with their own advantages. So as things got a little out of hand, we ultimately had to come up with an extreme measure, I would say, which was a coaxial test socket, or as some will call it, a metal test socket, where you have a metal grounding housing for shielding and impedance control. You have a dielectric material, usually a bushing, to suspend and center the conductor pin or the signal pin. And then you have a dielectric, usually an air dielectric in the case of an ATE test socket. Today, we're talking about an alternative, and that would be a coaxial or controlled impedance type of elastomer socket. So basically the same thing as a spring probe test socket. The big difference though, so you still have a metal frame or a metal web, if you will, or array plugged with elastomeric conductive materials. And then on the case of a signal pin, you have a dielectric material for impedance control and tuning. So the big advantage really of a coaxial type elastomer socket in theory would likely be cost because of batch processing. And that's really it. Of course, the shorter test or signal path would also matter with lower inductance and whatnot. But the main takeaway will almost certainly be the cost of ownership. So next we'll look a little bit at the SI performance comparisons between various test sockets. So here are some S parameters for a standard spring probe socket and a standard elastomer socket. They serve their purpose for many, many years until they hit a wall. But basically you have crosstalk, but you still have good insertion loss depending on the pitch and depending on the signal speed. And they were fine for quite a while, obviously. Then you look at coaxial spring probe sockets versus the coaxial elastomer socket. You'll find that they're very close in performance. We're seeing you're seeing very good return loss, mostly in mitigated crosstalk on both examples, especially at the 8 to 16 gigahertz range. But the biggest difference would be found in crosstalk. Obviously, insertion loss is almost the same. Return loss is very comparable. And then crosstalk, the advantage will go to elastomer.
Hey, Matt, this is a good time for asking a quick question.
Sure.
On this slide, can you explain the details of the crosstalk is much lower here than the spring probe? So you want to explain what is that related to? Is that only the height issue, the low inductance, or can you explain what is causing that?
Yeah, so I would assume, and so my understanding is that it's the lower signal path and lower inductance is the primary reason, and so and it probably also depends on any kind of stubbing you might have at the ends. So on the board side and on the device side or the DUT side, you might sometimes, depending on how well you shield the ball and or the spring probe. So not all coax spring probe sockets are alike, in all fairness. So some vendors do a very good job of isolating the signal path top to bottom, whereas others do not. So it really depends on which spring probe architecture we're comparing to. And so, I mean, if I'm going to be fair about it. So I would guess that it's a shorter signal path, possibly any kind of antenna effect from like a stub, and then inductance. Hopefully that
Thank you for that. So I have a second question. And
Sure.
that is what is the smallest metal core diameter on a single socket? And what's the bulk resistance of a single signal pin?
So your question is pitch? Is that what, or
No, it's the metal core diameter. Is when you were showing the picture on the second or third page where you showed the core diameter.
You're talking about the signal in the middle on the elastomer?
No, you have a core, then you have the insulator, and then
this one. Yeah, I'm not sure what our minimum is. I know that we've built these for at least experimental purposes down to 0.7 so far.
0.7 millimeter?
Right.
And what is the bulk resistance of a signal pin?
I have actually more slides for resistance values coming up.
Okay. So there's a third question that you have is what's the dielectric constant of the elastomer surrounding the pin and its tangent loss? Because I think in the picture here you have a dielectric material. So folks are very interested in knowing the dielectric constant of the elastomer surrounding the pin and its tangent loss.
Yeah, so unfortunately I don't know off the top of my head, but I can certainly find out. Anyone who wants to know or needs to know can contact myself or any of my colleagues, and we'll gladly answer what it is. But it should be some type of rubber. So it's obviously higher than like an air dielectric.
Okay.
Okay. Okay. On this slide, we're just looking at eye diagrams, and then as you can see, they're very comparable between both coax platforms. With the advantage in jitter to the coaxial elastomer. As far as, so here's the CRS question that you're asking. So this is over test cycles and then resistance measurements. So a typical elastomer versus a coaxial elastomer. So we're finding that it's slightly improved with, it's so slightly lower, but a bigger spread. So the average resistance is lower, but a slightly bigger spread or standard deviation between the two. Here's a comparison of all the socket types, resistance values over touchdowns plotted. So up to 200,000 contacts, mostly stable. So in conclusion, we're saying that crosstalk shielding, of course, is super important for these very high data rates. Spring probe and elastomer sockets both improve crosstalk, although we would argue that elastomer should present a lower cost of ownership over time. We believe that elastomer socket can further reduce crosstalk overall. And then we still need to do more physical measurements for the elastomer coax to compare our HFSS modeling and validate that. But basically, we think that there's a strong future for an elastomer controlled impedance solution.
We have another good question, which is can you please speak to the cleaning protocol recommended?
Yeah, so that's, in my experience, that's different depending on test floors and whatnot, but usually we would use some kind of cleaning pad, and then air, forced air is typical for elastomers in general. So it should be in line with a typical elastomer cleaning methodology, which is some kind of cleaning pad, adhesive cleaning pad, and then air.
But it's much harder to clean elastomeric pads, right?
I think it's actually, well, it depends. I mean, some would argue that it's easier. It depends. I mean, homogeneous spring probes are very easy to clean because you can be very aggressive, whereas a gold-plated spring probe is harder to clean because you don't want to be abrasive and you don't want to remove plating, basically. And so it really depends. So against a homogeneous, maybe it's slightly harder, but against a gold-plated spring probe, it might be easier.
Which one are you recommending here? Is it a gold-plated or is it the homogeneous?
For a spring probe socket?
No, not for spring. I'm not talking about spring probes.
Yeah, so
this is the elastomeric sockets.
Yeah, elastomeric sockets, we only have the various gold powder suspended in silicone is typical. So there's no homogeneous elastomer that I'm aware of.
Okay. And then there's a second question on what is the flatness and total deflection you obtained?
That's case by case, but I can't answer for this specific one, but I could get back to whoever needed to know.
Okay.
Sorry.
There's a question on ball pitch size in this modeling. What's the ball pitch size?
This should be based on 0.7 millimeter pitch. But again, we should have, obviously we should have been a little more thorough in explaining our experiments.
Okay. What about the lifetimes what is the typical lifetime for contacts during high temperature testing, and what's the effect of the contamination, especially for the high temperature testing?
So high temperature testing, like, I mean, that's a very hard question to answer even for a normal socket. I mean, it depends on so many variables, right? But elastomer is just mechanical touchdowns. We're getting hundreds of thousands depending on the application. So I think a lot depends on power density, how much current are you flowing through a single pin. So current carrying capacity, of course, comes into play. The environment, the cleanliness of the floor, the cleanliness of the package. So that's a very hard question to answer, which is why I think most vendors rely on mechanical insertion data, which is mostly static, right? And so in our case, we're getting hundreds of thousands on elastomers in general, but depending on the application, a 2 amp pin versus a 1 amp pin would be a very different outcome, right?
Is this a question that we should send to you so that you can give some specific answers later?
The high temperature question?
Yeah. Yes.
We can work with anybody on a specific scenario. We have a lot of equipment where we can run physical, we can do physical experiments. And then I think most vendors can also, including us, can also sample depending on the opportunity.
Got it. How did you control the jitter to be so small?
The jitter to be so small. I can't answer that question. I'm not an electrical engineer, unfortunately. But I can answer that if somebody would like me to get back to them.
Okay. I think the question that has come back is, elastomers always have a typically less travel distance than a spring probe. So what is the travel distance of elastomer you're showing?
I do not know. It's likely 0.2 to 0.3. So 200 to 300 microns is typical for an elastomer, whereas coax spring probes can be more than 500 microns or 0.5 millimeter. And so it just depends. And again, it depends on pitch and other variables. In this case, we're likely showing a 0.2 to 0.3 compression or stroke.
The stroke is 200 to 300 microns,
no,
right?
I'm speculating. I don't actually know. So that's from the hip, but that's pretty typical in the industry, is around 0.2 to 0.3.
So the question on this is the elastomeric probe, is it also suitable for cold and hot, cold test cycles? Because
it can, yeah, it can be. It depends on how hot and how cold, right? But I mean, if we're talking
you have
extreme,
a spec?
like,
do you have a spec?
We do have specs, and I can answer that question offline. But they should be rated to at least 125. And then I'm not sure on the minus side, but I can answer that offline if somebody wants.
Okay. So I think there's a question on planarity requirement for NPCB for elastomeric socket versus the spring probe.
Yeah, I mean, so the travel is less, and so it depends on how big the package is in the XY. And so the planarity spec, typically with elastomers, you want to have no solder mask over the LAN pad of the board. I think that's true of test hardware in general, but especially true of elastomer sockets. But I can provide that as well. But again, I don't have it offhand. I don't have it committed to memory.
Okay. Is there an array area limit of how big it can be?
There is. I don't know it off the top of my head. I know that we've made elastomers that are bigger than 40 millimeter by 40 millimeter substrate size.
So far, it's 40 millimeter by 40 millimeter?
I'm aware that we've made elastomers for packages bigger than that, at least in our company.
Okay. All right. Any last minute questions? I think these were the questions that I could. Oh, there is one other question I have missed, which is there a high risk of leakage or shorting to the metal frame caused by stray conductor film material?
No, I think it's a very low risk because we've insulated all the way through on the signal pin. Of course, we want the ground pin to short on purpose. And then we've insulated the power pin as well. So no, we think that risk has been mitigated.
Okay. When you showed the C-res slide, there's also a question on why does the C-res of the coaxial elastomeric pins vary less than that of the normal elastomeric pins? Difference between coaxial elastomeric pins and the elastomeric pins. Why is there such a big difference?
I would have to study the data a little more. I don't know that there's a big difference. If there's a difference, it should be pretty small. Of course, you can scale your data to make it look worse or better. But in this case, I don't think there was a big difference. I guess that would be my answer.
Okay. The last question we have is how many insertions are guaranteed?
I think everyone guarantees mechanical insertions. And so in our case, I know that we typically guarantee 250,000 mechanical insertions for our standard elastomer, at least. This elastomer, of course, is in development, so we wouldn't be able to put a number on that yet.
Okay. All right. Thank you, Matt. This excellent presentation, and thank you very much.
Once again, I would like to very much thank our sponsors who have made this event possible with their generosity and have also made it free to attend. Our premier sponsor, Cohu, our emeritus sponsor, Johnstech, our honored sponsors, ISC, iWind, and TSE, and our distinguished sponsors, Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec, SVTCL, R&D Altanova, UI Green, and our exhibitor sponsors, ELES, MJC, Phoenix Test Array, and Smiths Interconnect. Please, when you have an opportunity, thank them for sponsoring and making this event possible. And once again, we'd like to thank our premier sponsor, Cohu, the market leader in test interface solutions for the most challenging applications, and ISC, the global #1 total test solution provider. And with that, I will thank you all for joining us today and look forward to seeing you back here tomorrow. So thank you again for joining us and have a good day.
Thank you all.